Okay, I think we are good to go. Okay, welcome again. And this is going to be the last lecture for this course. I mean, like we might have an office hour on Tuesday, but this will be the last content of it. And even today's lecture, I mean, like I mean, to me, it's more to tell you about the number field sieve. And I mean, like I don't understand the number field sieve enough to sort of give a complete description of the algorithm. But the hope is that I can tell you enough to convince you that these ideas should work, and some of the ideas in it are actually they're quite clever. Okay, and the number field sieve is also something that developed over many iterations. So it started off with by Pollard, who felt that here is a potential heuristic to factor very special types of numbers that had a certain structure. Then he felt that maybe this is something he could use, and then that developed into what was called the special number field sieve. And then a whole bunch of people, Lenstra Manas, Karl Pomerantz, and several people got together and so on, and which eventually developed into the full-fledged number field sieve that is currently used in practice, especially for very large numbers, etc. So there's an entire book which is just called The Development of the Number Field Sieve, which has basically it's a collection of all the papers that went into the complete development of the number field sieve. And it is a pretty, it's a humongous algorithm, and there's a lot of things that go into it. There's only parts of it that I'm going to scrape in today's lecture. I'm going to give you just a high-level view of how the number field sieve works, so much so that I won't even be talking about sieving. Okay, let me just think of it as saying that it's a factorization algorithm that somehow uses these things called number fields. Okay, there is a sieving component to it, which like we were doing in Dixon's algorithm versus quadratic sieve algorithm. Both of them were L-half, but the whole point of the quadratic sieve algorithm was that we use sieving to reduce the constant that was in that thing. Here, we are not even going to attempt to do that. At this point, I just want to tell you that I want to get to L1/3. Okay, and I don't particularly care about what constant accompanies that L1/3. And at least even we're just going to assume that nature is going to conspire to somehow make your algorithm work, that all the nice things that you want to happen is going to happen. And then we'll sort of convince ourselves that, okay, if everything goes according to plan, then it seems like we have an L1/3 sort of. Okay, so let me just briefly recap about things that we have done so far. So we started with the Brilhart-Morrison approach of doing this, coming up with a congruence of squares sort of approach to do factorization of integers. And as you recall, congruence of squares was something that was attempted a long time back. It goes all the way to Krajcik, and even Fermat had attempts to come up with congruence of squares, etc. And it was really the first effect. I mean, some sort of reasonable way to make it effective was done by Brilhart and Morrison. And Dixon's algorithm was a rigorous analysis of such a factorization algorithm. And the quadratic sieve is something that which improves the constants, which is and so on, but it's based on some heuristics. So from this point onwards, many of these algorithms are going to be based on various kinds of heuristics, where we'll sort of say that within a certain range, I expect numbers to be roughly smooth, as if you're picking these things at random, even though you may not be picking things at random, etc. Okay, so roughly speaking, what we did was the following. We picked a whole bunch of i's, such that this was my ai and yi. I'm describing the quadratic sieve, how the quadratic sieve proceeded. So, and you just notice that ai squared is equal to yi squared, just by construction, mod n at least. Okay. And the point is, you try to find many such i's, such that this yi that you end up getting happens to be B smooth. Okay, and by B smooth, I just mean that all the prime factors that this yi has, it's all bounded by at most this bound capital B. Okay, and once you know that it's a B smooth number, you can sort of factorize them either by trial division, or you can do something a little cleverer. which is what we did in the quadratic sieve, by somehow amortizing the cost of factorization throughout. Okay, and what was the point of doing all this? Because I want to find, I mean, AI squared, AI squared is equal to yi mod n by construction. So the AI squareds are naturally squares, but I'm trying to somehow find a product of these yi's which also happen to be a square. And how did we do this? We basically took the exponent vectors which corresponded to the factorization of each of these yi's, put them all in a matrix. Let's say they are rows of a matrix or something. And once you have enough relations, you will be able to find some subset of rows, some non-empty subset of rows, such that this product happens to be a square, which is basically just solving a system of linear equations modulo 2. So you solve that system of linear equations, and that will tell you, okay, take this particular product of these yi's, it happens to be a square because all its exponent vectors, the exponents are all even numbers. So that naturally tells you that if you take x to be equal to the product of ai's and y to be equal to the square root, which you know exists, it's a legitimate number, okay, then you know that x squared equals y squared. Okay, and therefore you're now hoping that when you take the GCD of n with x plus y or x minus y, well, hopefully one of them will be some non-trivial factor of n, and then you get that non-trivial factor. So this was a high-level picture of how all of these factorization algorithms we have seen so far worked. Okay, so let's just try and do this fantasy of, no, suppose I want to beat this L half. I want to go somewhere below L half. Okay, and we want to get a sense of, what can I do in this process? And one thing that really helped is that in Dixon's algorithm, we were picking these AIs completely at random, and the yi's were basically AI squared mod n. And so we basically said that, oh, all of these yi's are basically like, it looks like a random number from 1 through n. Okay, the advantage of doing what Morrison-Brilhart did, or what the quadratic sieve does, is that the yi's are much smaller than what sort of yi's you end up with in Dixon's algorithm, because here yi's are roughly going to be about root n size, especially if I was small. Okay, now suppose magically it so happens that you can make yi's to be as small as something like n power 1 over d, where d is something that you can control. So far we have been working with d equal to 2 in the quadratic sieve, so that you have yi's that are roughly about root n or something. But I don't know, maybe you can make it n power 1 by 100 or n power 1 by something that also grows with n. Something, I mean, let's just work with this fantasy. So then let's just see what can we do with such a thing. So let's again leave this floating, the bound of the smoothness that we want. Let's just say I want this to be some L of s comma beta. I'm trying to figure out what is the best S that we should choose eventually, once we optimize a whole bunch of things. Okay, so most of the time what happens is that the most costly step is this data collection step, because you're trying to build many congruences of a certain type, and many of the attempts will not even give you a smooth number. So you might have to pick it once more, etc., etc. Okay, so roughly speaking, how many congruences do we need? We need a little, like around b of them. It's like we need as many congruences as the number of primes in 1 through b plus 1, which will throw away log factors and say that we need b congruences. But there is also like the number of samples for every smooth congruence, because when you pick this y at random, it's not going to be likely that the yi you end up with is a smooth number. So okay, so you need to account for the fact that the density of smooth numbers is not too many either. Okay, so putting them both together, what do you end up with? So the number of congruences we need, this is exponential in beta log n to the s log n to the 1 minus s. I mean, I'm just writing ls beta explicitly. Okay, and what about the time taken per smoothness? If you recall what this used to be, this is going to be 1 minus s by d beta into log n to the 1 minus s log n to the s. Okay, this comes from the fact that you are working with things up till n power 1 over d, which I'm approximating, which I'm writing it as L of 1 comma 1 over d. Okay, and if you remember if I want numbers in this range and I want it to be this smooth, how many samples do I need until you pick that? That will turn out to be an expression of this sort. Okay, now again, let's work with this fantasy and let's assume that d is roughly about cube root of log n. Okay, why this is optimal, etc., is completely unclear at this point. We're just playing along to see what this calculation would yield. So let's just give this a name. Let's call this star. Okay, so what does star become? So star is going to become exponential in beta log n to the s log n to the 1 minus s times exponential in something like 1 minus s over beta, which are all constants. Okay, so I'm just writing this as 1 minus s over beta. And now let's see what happens. I have a log n to the 1 minus s here. And this d is going to contribute a log n to the 1/3. Okay, in the denominator, which means I'm going to end up with log n to the 1 minus s minus 1/3. And the same reason, so this is going to be log n to the s plus 1/3. Okay, and what is this? This is L of s comma beta, and this is L of 1 minus s minus 1/3, comma this 1 minus s over beta or something. Okay, and now if you want to say, okay, so far we had kept s floating, we need to figure out what is the best choice of s that minimizes this product as much as possible. Basically it makes sense to choose L such that this s equals 1 minus s minus 1. Okay, and if you work with that, you basically get at s equal to 1/3, we get L of 1/3 comma something. At this point, I don't care about the constants that are there at all. So we get L 1/3. Okay, so all of this is just a fantasy. It's just a fantasy to somehow say that if we somehow manage to work only with numbers of size about n power 1 over cube root log n, okay, some weird number of this sort, as long as we are dealing only with that, and somehow if you can come up with a way of adapting your factorization algorithm to only ever look at numbers of this magnitude, then it seems like we can actually get to L1. Okay, so the whole point of the number field sieve is not to try and see if we can somehow realize this fantasy. Like, can we somehow make sure that we deal only with numbers of this type? Okay, and one of the cool ideas of Pollard was to basically say that okay, we may not be able to do it as long as we work with integers. We might have to move to a slightly different world of what are called these number fields. Okay, so what I'm going to do is I'm going to take a short aside. I'm going to tell you a bit about number fields, but just as little as possible about number fields until I can I can describe the algorithm. Okay, and I'm going to only tell you the things that make it useful for the exposition I'm going to give. The whole study of number fields, in some sense, is it's this entire field of algebraic number theory. Much of algebraic number theory is about the study of number fields. So clearly, this is a really vast topic, and I may not be able to do justice to the whole topic, obviously, in one lecture. But I'm going to tell you the bare minimum you need, and just throw so many things under the proverbial carpet. Okay, and just to give you just the high-level details of things. Okay, so what is a number field? So a number field, in some sense, is basically fields of the following type. You take your rationals and you go modulo some irreducible polynomial where f of x is some integer polynomial. Okay, in many instances, in fact, you will choose this to be an irreducible. I want this to be irreducible. Otherwise this won't be a field. Okay, so I want it to be irreducible. And in many instances, you might actually choose it to be monic. Okay, but in general, when we are talking about number field sieves, f is not expected to be mnemonic. Okay, and things of this type are called number fields. Okay, so like for example, if you want to look at fx quotiented with x squared plus 1, okay, it's like as if to the rational numbers you are adding the complex number I. Okay, you are like adding one root of f. So in some sense, this is equal to q alpha, where alpha is a complex root of f. It behaves like that. So in some sense, there is no real difference between them. So in some sense, x is playing the role of alpha. Okay, this is what a number field is. Okay, now the reason number fields are so interesting is because they happen to share a lot of similarities with the rationals, especially from the context of factoring. Okay, but one needs to take care a little bit here because everything is not rosy, but nevertheless, a lot of interesting properties seem to happen. So the first thing is K contains a ring, which is often called OK, of integer-like elements. Just like the rationals contains within it an integers, it so turns out that these number fields also contain within it something that looks like integers. Like, what do I mean by something that looks like integers? Because within this OK has a notion of primes. Okay, just like integers has this property that every integer can be written as a product of primes, a finite product of primes. And turns out OK also has this property. It's just that you need to suitably change your notion of what prime means. But there is a way in which the integer-like elements inside the number field somehow split in terms of these primes. Okay, in a sense that any element of OK can be written as a unit. A unit is nothing but an element in OK that happens such that the inverse is also in OK. You know, it's like our 1 and minus 1 that we are more familiar with. Okay, a unit times a finite product of primes. Okay, just like we are familiar with integers. Okay, each of these integer-like elements can be written as a unit times a finite product of primes. Okay, so let's just look at a few examples to just get comfortable with what these things are. So one of the things that we mentioned was just the thing where if you quotient with x squared plus 1, then it's like as if you're adding the complex number I to it. So what are elements in this thing? It's basically things of the form p plus qi, where p and q are both rational numbers. Okay, that's it. It's just complex numbers where the real part and the imaginary part happens to be rational numbers. Okay, now turns out this OK is basically z comma I. I mean, the polynomials involving I, which is basically the set of all a plus bi, where a and b are both integers. Okay, so it's just that the integer-like elements inside this number field are basically complex numbers where both the coordinates happen to be integers. Okay, now can someone tell me what the units in this are? What are things where, what are elements in OK such that its inverse is also in OK? Certainly 1 and minus 1 are examples, but are there more?
Is it like their the value will be some absolute value will be also 1, something like that?
I mean, right now Okay, hold this thought, because this absolute value is something that we haven't formally defined here. But I guess you're talking about the length when you think of it as.
Yes.
Yeah. Okay. So then, yeah, maybe the
My
length has.
question was that given a field, is there any algorithm we can show that how many this kind of OKs are there, something like that?
Yeah. So Sage has everything. You define a number field, you say, tell me the ring of integers, it will tell you what the ring of integers are. You can say, tell me the units, it will tell you what the units are, everything.
So is there is there any, I am trying to say that if we progress that, if we choose the field of finite fields of n elements, so is there any sequence which is there given
Sorry, I'm a little confused. So number fields are always extensions of the rational numbers. You start with the rational numbers and then you're adjoining one of these complex roots to it.
Yes.
So, I mean, none of this is finite because they always contain Q.
But we can have an index number, right?
Sorry, what do you mean by index number?
Means every field, whatever we are doing, one can be embedded in other, right? So if we take the quotient with that, so we can divide it in also in finite number of steps, right? In finite number of posets, right? If we see.
Sorry, divide what by what? By the way, so I mean, are you talking about a general thing or is it related to what we are doing today?
Yeah. I am talking about this only. So is there this algorithm to find the number of quotients? If we take our rational field in another rational field, finite field.
I mean, I'm very confused. When you're talking about rational field, why is it finite at all?
Okay, I'll discuss you after the class.
Okay. Okay. So the units in this. Oh, sorry, I had asked this question and then I just forgot that I had asked this thing. But it would, I mean, it's sort of easy to sort of see that the units are, of course, 1 and -1. The traditional units in integers are units here, but you have 2 extra units, which is I and -I. Okay, because they happen to be inverses of each other. Okay, so this is just an example to sort of say what happens in this. But here is interesting. Here's something interesting. Let's try and get a sense of what are the primes here. Okay, let's take our traditional primes and see which of them are actually still primes in this thing. So a prime is just something that can't be split up any further. So a number is prime if it can be written as a product of 2 integer-like elements, then one of them has to be a unit. Just like we would do in the integers. There is no way to really split it into 2 other non-unit integers. Okay, so now let's ask ourselves, is 2 a prime in this place? Or can you come up with a way of writing 2 as a product of 2 other elements?
I think I'm just sort of confused about what are we allowed to do now. So we have.
So I want to know. So the integers are basically, these are my new notion of integers in this world. Can you write 2 as a product of 2 integers? Of course, you're not allowed to write it as -1 into -2.
1 plus I and 1 minus I.
Excellent. So this actually splits as 1 plus I and 1 minus I. Okay, so 2 is actually not prime here. Okay, so instead of 2, it turns out that these 2 things are, so I have 1 plus I and 1 minus I. These happen to be prime numbers in this world. Okay, now 3. So it turns out 3 is prime in this world. Okay, what about 5?
4 plus 2 plus I and 2 minus I.
Good. So 5 is also not prime here, but instead I'll have to write 2 plus I and 2 minus I. And so on. So what's happening is that some of the primes that you are more used to turn out to stay as primes. I mean, the traditional integer primes end up being primes. But some of these primes actually happen to split in this world. Okay, so the notion of primes here is going to be slightly different. Okay, so I'm just saying some traditional primes are primes and some split. Okay, so I mean, this world is a little different than what is happening in general. Okay, and here is this is something that is usually not the case, but some important thing is that this particular number field, which is Qi, actually happens to be a unique factorization domain if you define unique factorization properly. Okay, what does unique factorization mean? Any integer can be written as a unique product of primes, in a sense that if somebody gave you a different product of primes, you can relate the primes using multiplication of units. Like, you basically want to say writing 6 equal to 2 into 3 and minus 2 into minus 3. I mean, they're both the same thing. Why are they both the same thing? Because you can relate 2 to minus 2 by saying, oh, you just multiplied by a unit. And you relate 3 to minus 3 saying, oh, you just multiplied by a unit. Because notice that 2 plus I into 2 minus I, this is equal to 5. Well, so is 1 plus 2i into 1 minus 2i. This is also equal to 5. And one could say, oh, it's not a unique factorization because I give you two different factorizations. But just notice that, if I multiply this with I end up with this. If I multiply this with I end up with this, and so on. Right? So therefore, they're basically the same factorization. Okay. So this is what happens. So let me formally define what things are, because we kept saying that, there are these integer-like elements. What the hell does that mean? I mean, integer-like in what sense? Okay. So this is formally defined as saying that a complex number is said to be an algebraic integer if it happens to satisfy a monic irreducible integer polynomial. Okay, these are what I'm going to call integer-like. Okay, so here are some examples. Of course, our standard integers are all integers because they satisfy the polynomial x minus that integer. It's a stupid polynomial that it satisfies. But you also have things like root 2, root 3, cube root of 5, etc. because the polynomials they satisfy are things like x squared minus 2, x squared minus 3, x cubed minus 5, etc. And then you have things like this, minus 1 plus root 5 by 2. They seem to have rational numbers associated with them, but this is like the golden ratio. It satisfies, I think the polynomial is x squared minus x plus 1 or something like that, or x squared plus x plus 1. So yeah, so these are what integer polynomials are. And something that is not obvious on the face of it, which is that if you actually add two integers, you get an integer. And if you multiply two integers, you also get an integer. Okay, it's not obvious because if alpha satisfies a polynomial mu x, which is an integer monic irreducible polynomial, and beta satisfies some other mu x, I mean, firstly, it's not even clear what is the smallest polynomial that alpha times beta satisfies or alpha plus beta satisfies, and why the hell should it also be a monic integer polynomial? But turns out it is. Okay, and turns out it forms a ring. I'm not going to go into the proofs or anything of this sort. So now you know what integer-like elements are. And now, if we have a specific number field in mind, the integer-like elements are which are the integers that are present in this number field. That's it. Like among things in the number field, which of them satisfy a monic irreducible polynomial? Okay. And then a definition of prime, like I mentioned earlier, is that we will say a particular integer or whatever integer inside a number field is prime if whenever you manage to write it as a product of two other integers, one of those two must be a unit. Like there is no way to split up this integer into two non-units. Again, very similar to what you would have done in standard integers. Okay, so I mean, on the face of it, it all feels like, this seems very nice, like it basically seems to behave like integers. We seem to have factorization, etc., etc. but there are a whole bunch of things that could annoy us. Okay, so firstly, I gave you one example where the set of integer-like elements was just zi, in the sense that you're actually looking at just polynomial expressions where all the coordinates happen to be integers. This is usually not the case. The ring of integers could sometimes be completely nasty. Okay, there could be all sorts of weird elements here. I mean, if you thought this was a weird example of an integer, I mean, you ain't seen nothing yet. I mean, there are all sorts of crazy things that could happen. And secondly, even among the units, there could be infinitely many units. Okay, you could end up with crazy situations where the number of units even is very, very large. Okay, in fact, the units often form a group, and all I might be able to say is that they are generated by these things. But there could be many of them. There could be lots and lots of them. Okay, and thirdly, I gave you an example where you even had unique factorization, which is usually not the case. All I can tell you is that there is a factorization. There is no uniqueness that I can usually guarantee. Okay, and this is just again scratching the surface. There are plenty of other issues because eventually we'll want to do computations on them. And many of them may not be suitable for computations. Okay, in the sense that things that we may want to do is something that it may seem difficult. Okay, but again, hopefully, at least even though I tell you that the typical number fields could be very nasty and stuff like that, I just want to give you an example of how factorization may be. I mean, you can come up with factorization algorithms if your number field behaves in a very, very nice way. Okay, so I'm going to take one example. Okay, and I'm not going to work out an example, but I'm just going to tell you a sense of how the number field sieve works, because it's one of these examples that's as rosy as possible. Like all the nice things you want from the number field, they all you have that somehow. Okay, so the number that I want to factor is 16259. Okay, and I'm going to choose the following specific polynomial. I know you will have questions. You'll be like, where the hell did this come from? But I will try and answer them shortly. But just play along with it because I just want to give you the template of what happens. Okay, we're going to choose this as our polynomial, which fortunately happens to be irreducible. And it's a monic polynomial also. And this is my number field. Okay, if you care about what exactly are the complex roots of this, the complex roots are 1 plus minus square root of minus 11 by 2. Okay, and let's say alpha is going to be this 1 plus square root of minus 11 by 2. Okay, so the thing is, turns out a bunch of nice things happens. Okay is basically Z alpha, like you want. I mean, like, this is a nice thing to have, which is if I ask myself, what are integer elements here? Well, it's basically integer linear combinations of this kind. That's it. Okay. And furthermore, and it is UFD. It happens to be a unique factorization domain. And units, there are only 2 units, which is plus or minus 1. Sorry, plus or minus 1. Okay, so all the technicalities that I was talking about that happens for a general situation, none of them happen here. It's a very clean sort of system. Okay, and here is one more rabbit out of the hat. I'm going to say that I actually chose this polynomial carefully, actually, because if I choose m to be equal to 128, okay, m squared minus m plus 3 happens to be equal to this. So in particular, it is 0 mod n. Okay, so again, it's again a very weird thing to say that I chose a polynomial and I chose an m like out of thin air at this point, but this is going to be important that m is a root of f of x mod n. Intuitively tell yourself that m is almost like this complex number alpha as long as you're working modulo n. Because m satisfies the same relation that alpha seems to satisfy. Okay, so So far, it just feels like, some random things that we have done here. And now let's go to the main step, which is the data collection step. So what I'm going to do is the following. I'm going to find a whole bunch of pairs. I'm going to try out, just like we tried out in all of the previous factorization algorithms, such that the following two numbers happen to be smooth. Okay. You know what smoothness means here. This is an integer. AI minus MBI is some integer. And we know that smoothness just means that, all the prime factors are smaller than some predefined bound that we will have. What is unclear is what the notion of smoothness means, but let's play around right now. We know that this does get factorized into a bunch of things, bunch of primes. If we could somehow associate, I don't know, the magnitude of each of those primes or something, we might be able to say that I only want small prime factors in this number field. Okay. So now what we are going to do is we are going to try and factorize both of them, because I'm only picking up all of those AIs where the AIs and BI such that these two things, A minus MBI and A minus alpha BI, both happen to be smooth. So therefore they only have small primes. So what we'll do is we'll put them again into a matrix. But now we need to be a little careful. We need to figure out how many negative numbers showed up here, because I eventually want a product of them to be a square. Okay, so there's a whole bunch of primes which are the integers. These are the exponent vectors in integers. And these are the exponent vectors when it comes to primes in this number field. Okay, we'll write down this thing. And now I'm going to try and find some row combination that basically sums to 0. So sums to 0 mod 2. Okay, what is that going to tell me? It's going to tell me here is a product of these AI minus MBIs, which is a square in the integers. And here is a product of AI minus alpha BI, which is a square in OK. So that's what I end up with. I found two squares. Firstly, it's not even clear why the hell are they the congruent to the same thing mod n or anything. There is no mod n here at all. It's some bloody number field. Okay. And so here is an example. So if you take R of Z to be this weird expression, I took all of these things. Okay. And if you, these are the, there is one corresponding to A equal to 3, B equal to 2. Then A equal to 7, B equals minus 3, A equal to 8, B equal to 1, etc., etc. If you look at R of M, which is 3 plus 2M, 7 minus 3M, 8 plus M, etc., etc., and you factorize it, you end up with this. Okay. On the other hand, if you look at 3 plus 2 alpha, 7 minus 3 alpha, 8 plus alpha, etc., etc., and you factorize it, you get this. Don't ask me how I found it. I actually found the lecture notes. I'm just copying it from there. Okay. But the point is, computationally, this can actually be done. But suppose this happens. Okay. What does this mean? Now what I'm going to do is I'm going to set X to be the square root of this guy, which is just 2 power 4 times 3 times 7 times 13 times 17 times 19 times 29 times 37, and go mod n. Okay, that number is 14,100. Okay, now what do I need to do about y? So again, I can take the square root of whatever this thing is. So that's what this y is here. But this is not what I want. I want a number modulo n such that x squared equals y squared mod n. So here is where the choice of that m matters, because what I'm instead going to do is, instead of taking this number, I'm going to end up taking the following: m squared into 1 minus m power 4 into 1 plus m into 2 minus m the whole cube into 1 minus 2m into 5 minus 3m. Okay, and the reason I'm doing this is mentally, modulo n, alpha and m are not very different. They satisfy the same relations. Okay, because we chose m such that m also satisfies f of m equals 0. Okay, and if you actually calculate what this is, this turns out to be 7426 mod n. Okay, And because M satisfies the same relation that alpha satisfies, it turns out that x squared is equal to y squared mod. Okay, and if you take the GCD of these two, you get one of the factors, which is 70. Okay, so this is just a high-level picture of how a number field sieve would work, assuming somebody gave us this advice of what to do at each of the steps. So obviously, you might have a lot of questions. The first question could be, how the hell did I choose my f of x and m? I mean, I seem to have just pulled it out of thin air. Okay, so that's question one. Second question, what do you mean by small primes? And how are you going to factorize things inside the number field? Okay, because it feels like a lot of things seem to go right for this to work. Okay, but besides these, do people have other questions, things that feel very mysterious and so on?
I'm just kind of like, I got what's happening, but like what, like at least at the outset, what suggests that this might work better than the quadratic sieve?
Good. So just okay, a spoiler for this is that in order to get the same sort of okay, so let's think about what's happening in the quadratic sieve. Like, I mean, so one of the things you could do is the factor base that you have. That is what is your smoothness bound? You could potentially have made it much smaller. I mean, we chose it to be L half, but you could have in principle taken it to be far smaller. Then all of these matrices will become smaller. Where do we get a hit? We get a hit because we are trying to collect pairs such that we are trying to collect these smooth congruences. And most of those congruences will not be smooth. So you'll have to try a lot more samples. And we basically wanted to say, oh, but that may have been okay if it so happened that the numbers you're testing for smoothness was very small. Right? Which is where instead of numbers being up till n, the fact that we made it up till root n, that was already helping us. But now the key difference is going to be that I can afford to take these AIs and BIs to be way smaller than what it used to be in the quadratic sieve. So the sort of numbers I'm trying to look for smoothness is just going to be of the order of n power 1 over t eventually, which is something I don't know how to do just using the Morrison-Billhart sort of approach. And the whole point of the number sieve is that just by dealing with numbers where these AIs, BIs, and Ms are very small, you might still be able to do more or less what you wanted. And that's where your improvement is going to come. Okay, so towards the end of the lecture, we will see a calculation as to exactly where things happen the way it happens. Okay, and this one is always a little mysterious, but I'm going to sort of be a little imprecise about it. I'll just maybe say something. If it doesn't make sense, it's okay. So the point is, there is a homomorphism from this number field, Q alpha to Z mod NZ, which just sends alpha to the integer M or M mod N, just because of the fact that alpha satisfies the same relation that M satisfies. So this was actually an element in the number field. So we just applied this homomorphism where I just replaced alpha by x, and then I got whatever. So that's the reason why x squared is equal to y squared mod n in the way we have constructed. But I'm not going into too much details about that at the moment. Okay, but I hope it seems to at least smell right, that what we are doing is going to somehow give us a congruence of squares, assuming, of course, all the other nice things happen. Okay, so what I'm going to try and do is I'm going to try and give you some hints as to how do you do each of these steps. Okay, actually, the first step is actually not hard at all. The point is, it just feels like these polynomials came out of nowhere, but we're going to choose fx and m such that I know for a fact f of m is equal to 0 mod. And here's what I'm going to do. I am given an integer n. My goal was to factorize this integer n. Okay, so what I'll do is I'll split this n into a bunch of blocks. Okay, let's say about d+1 blocks or something. Okay, that is, I'm just taking the binary representation of n and just chunking it up. And what do I know right now? I know that this n is equal to something like ni times, I don't know, 2 to the L times I. Right? Because something is here, it is this times 2 power whatever, plus this times 2 power that squared, etc., etc. I mean, we are literally just writing the number in base 2 power L. Okay. And this L is also, I mean, like, so basically what I'm going to do is I'm going to choose roughly 2 power L to look like something like n power 1 over d. So I'm splitting it into something like d blocks. Okay. And now it's clear what I want to do. I'm just going to set m to be equal to 2 power L. Okay. And my polynomial to just be equal to n0 plus n1x plus blah, 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 till whatever, n, I mean, nd 2 to the d. And just by definition, if I plug x equal to 2 power L, it satisfies this. Okay. So clearly, f of m is equal to n, which is equal to 0 mod n. So that's it. I mean, like, well, basically, we're just going to take the representation of n, chunk it up, and build our polynomial based on that. If you want a degree 3 polynomial, we'll split it into 4 parts. If you want a degree 7 polynomial, split it into 8 parts, etc., etc. Okay, but of course, we wanted f to be an irreducible polynomial, etc. Okay, so we now pray that the polynomial that we ended up constructing in this process is an irreducible polynomial. Okay, again, this is a heuristic. For now, let's just assume that nature works in your favor and tells you that this polynomial is actually an irreducible polynomial. Actually, this is one of these things where if it is not irreducible, turns out factoring is far easier. Okay, but for now, let's just assume that it's an irreducible polynomial. Okay, so this solves the problem of finding the polynomial f and finding the integer m. So are there any questions at this point? Okay, so at least now we know what number field we are working. Okay, based on the number n, we are now going to choose our m and n. So this is also why, you know, the choice of m that we had in the previous example, we chose it to be 128. This was an example where 128 made sense because it's a usually it's a power of 2. Okay, good. Now the next thing I want to tell you is a notion of what do you mean by small primes? What is the magnitude that you're going to have? Like, what are you going to associate as the length of one of these algebraic integers, etc.? Okay, there are usually various definitions you could have, but there is one which is very, very useful from the perspective of this number field sieve. But rather than tell you exactly what the definition is, I'm first going to tell you what you want from this definition. And then we'll try to see if we can come up with a definition that satisfies the properties that you want. Okay, so what I want is a way of assigning a rational number to every number field element, which is going to basically say, oh, this one is this big. Okay, this guy's length is like 3.5. This guy's length is 7. Okay, so that's what I want to say. And what are the properties I would like? I would like this norm to be multiplicative. In the sense that the norm of xy, I want it to be the norm of x times norm of y. I mean, this is usually what you would expect in any sort of length type calculation. Okay, and of course, any self-respecting norm, 1 must have unit norm, 0 must have 0. Okay, this is something that I would like. And something that will be very useful is that I would also like that whenever I give it an integer element and ask what is the norm of that, that actually happens to be an integer. Okay, so that the norm is giving me some indication of am I holding an integer or am I holding just an arbitrary number? Okay, and something else which would also be useful is that a norm of any prime also gives me a prime. Okay, and this is like sort of. Okay. In fact, what will happen is that one of these non-standard primes that we had, like 1 plus alpha, 2 plus alpha, etc., that we had, those will end up going to primes. The traditional prime might end up going to a power of a prime. That's usually what happens. Okay. So this is something that, this is a sort of notion of length that I would like, because it allows me to think of prime numbers as basically prime integer length numbers, and integers as things with integer lengths and etc. Okay. So how do you define this norm? Okay. And of course, okay, let's do one maybe a pop quiz before that. Suppose you pick up a unit just based on these axioms. What can you say about the norm of the unit?
I didn't get the question. Can you repeat it?
So right now I'm basically saying norm is some function. I haven't even told you what this function is, but these are the axioms that I have told you about the function. Okay, all of these. That is, it sends an integer to an integer value. It's multiplicative. One goes, I mean, the norm of 1 is 1 and the norm of 0 is 0. So this is all you know. But from this, can you infer? Suppose you know that u is a unit. What should its norm be?
1, right?
Yeah, can you say why?
Okay, so basically, if u is unit, then there will, its inverse also will be unit, right? So norm of 1 into norm of 1, that is
Right.
if using the multiplication norm of u into norm of u inverse, and norm of u inverse is also will be 1, means also will be norm of u.
No, so in fact, so this can be written as norm of u times norm of u inverse.
Yes.
Okay. Now I'm just going to use the fact that norm of any integer is supposed to be an integer.
Yes. So that means,
so I know this is an integer. I know this is an integer. And apparently a product of two integer equals 1.
Yes. So that
So it
means
better be the case that the norm is plus minus 1.
yes, either plus or minus 1.
Good. So, okay. So this, just to sort of say that just these axioms already tell you that the norm has to be plus minus 1. Okay, good. So here is how the norm is actually defined. And I think this is a spoiler to one of the questions in problem set 3, but nevertheless, I'm going to tell you what it is. So here is the number field, which is this Q alpha or something. But what are elements here? They're basically things of the form something plus something times alpha plus something times alpha squared all the way till d minus 1 or something. Right? So you can think of that as a vector just based on what are the coefficients involved. Right? So this is also a vector space over Q of dimension d, because every element in this number field is basically a d tuple of elements. That's how you specify it. So now I'm going to define a function, or rather a map here, which is, so let's say you pick some particular beta in this number field whose norm I want to define. I mean, this whole point is to define the norm of beta. Okay, so here is what I'm going to say. So here is the mult of beta, which is something that takes an x. Okay, maybe I shouldn't use x. I'll say it takes an r and just moves it to beta times r. It's just multiplication by beta. Okay, now this is a linear map, right? Because multiplication of r1 plus r2 is a multiplication of r1 plus multiplication of r2. So when you're talking about a vector space and when you talk about a linear map, there are a bunch of axioms that it's supposed to satisfy. And of course, multiplying by beta satisfies all of those axioms. Okay. Now you just define norm of beta to be the determinant of the matrix corresponding to this linear map. because any linear map from the vector space K to the vector space K will have some matrix representation. Just look at that matrix representation, take its determinant, and we'll define that to be the norm. So I'm saying it's a spoiler because now you know why a trace is called a trace. Because what you're actually doing is looking at the trace of this matrix representation. Okay, so this is a slightly weird concept. In fact, norm can be defined in many other ways, but I'm going to, okay, so this also tells you why trace is called so. Okay, so let's just look at a couple of examples. In fact, these are examples that you will actually be familiar with. Okay, so now let's take our usual, adding just I. We are looking at A plus IB, complex numbers where both the real and imaginary parts are rational. Okay, so if I want to write multiplication as a matrix, okay, how would I write this? So the standard basis for this thing is everything is of the form, I don't know, P plus IQ. So it looks like the basis is 1, I. That's what the basis looks like. So I need to tell you, if I were to multiply A plus IB with each of the basis vectors, what do I end up getting? Well, if I multiply it with 1, I will of course get A plus IB, which is represented as the vector A, B. Now, if I multiply it with I, what would I end up getting? I would basically get minus B, A. So that's what the multiplication operation with this complex number looks like. And what's the determinant of this? This is A squared plus B squared. So now you know why the norm of a complex number was defined. I mean, the Euclidean distance made a lot of sense, but there is also an algebraic meaning to why the norm is A squared plus B squared. Okay, now let's try a different example. Suppose your number field was actually Q root 2. Okay, and now I have a complex number, sorry, I have one of these elements of the form A plus B root 2. What is the matrix representation of this going to be? So the first column is usually just A and B because I want to know what's the image of 1. What's the other basis element? The other basis element is root 2. So when I multiply A plus B root 2 with root 2, I actually end up with 2B plus A root 2. So I have 2B and A. Okay, and the norm of this is going to be A squared minus 2B squared. I mean, this is the definition of what the norm is with respect to this field. Okay, so hopefully you at least now know what a norm is. And because it's the determinant, notice that norm is naturally multiplicative. Because multiplying by beta followed by multiplying by gamma is the same thing as multiplying by beta gamma. And the determinants will nicely multiply together and so on. Okay, so all the other nice things continue to happen. Okay, and just take it for granted. Again, I mean, you can actually calculate it if you want. But the thing that we'll need for the number field sieve is the following, which is that if you're looking at elements of the form A minus B alpha, these are the sort of elements we were looking at in the factorization algorithm. Its norm has a very nice representation in terms of what this polynomial f is. Okay, it's just this, it's almost looking like, writing f in its representation, but it's some homogeneous version of this. You have A power D minus 1, D all the way to B power D. Okay, just take this for granted for now, and let's just proceed with the final big part of the puzzle, which is how the hell do you factorize here? I mean, how are you supposed to factorize things in the number field? Okay. But maybe before that, I'll just pause for a moment to see, are there any specific questions, etc. I mean, I know there's a lot of new things I'm throwing at you, but just play along. I mean, as long as something doesn't smell right, let me know. And if it seems believable, let's just proceed. Okay, finally, how the hell do we factor in this number field? Okay, and here is a really cool idea, which is let's factor the norm of A minus B alpha first. Okay, so here is the thing. I want to factor this number with this number field element. Okay, suppose I compute its norm and I get to know that the norm of this is actually, let's say 15. Okay, now that tells me that if at all it's a multiple of things, it has to be a multiple of some prime of norm 3 and some prime of norm 5. Because we know for a fact that any integer will go to an integer norm. Everything is multiplicative. So if the norm splits as 3 times 5, then it basically is telling me that, oh, that must mean that, whatever is the split of this guy, it must be something that had norm 3 and something that had norm 5. Okay. Now, the point is, it may be the case that there are many primes in this number field that have the same norm. Okay. But fortunately, there aren't too many of them. Okay. So let's factorize the norm this first. And we are basically saying that if P divides the norm of A minus B alpha, then some prime, I'm going to write a weird box version of P, okay, of norm P divides A minus B alpha. Okay, now turns out there are at most D primes that have norm P. That is, once you fix a prime and you ask, how many different primes do I have that has this norm P? Turns out there are really just D distinct primes. At most D distinct primes. Again, D is the degree of the polynomial that you have. Okay, so just like if you recall the example, we had 2 plus I and 2 minus I. I mean, the number 5 split as 2 plus I and 2 minus I. The norm of both 2 plus I and 2 minus I are both equal to 5. Because 2 squared plus 1 squared is equal to 5. Okay, and so there aren't actually too many primes of any fixed norm. So we can actually afford to enumerate them. And check. Actually, there is a cleverer way of doing it. You can actually identify which prime even is there. So this is roughly how factorization works. The way we are going to do factorization is, before we even try to factorize the actual number field element, we compute the norm, factorize that. That is going to tell us what sort of primes to even look at. And then we'll figure out, okay, I know there is a prime of norm 5 that divides it. I don't know which one it is. I will try all of them. There's a different way of even figuring out which one it is, but let's not move into that. And in this entire thing, I'm completely forgetting that there are these things called units. Okay. And again, we're going to pray that these units don't create an issue. Okay, because we are not going to get a factorization that just looks like a product of primes. It will be a product of primes times a unit. Okay. And we're going to assume that the units don't create an issue. They actually do. In fact, much of the trouble is because of these damn units. But let's assume that these units don't create an issue. Okay. Now that the basic parts are done, I can now tell you a slightly less unprecise definition, description of what the number field sieve actually does. Okay. And we'll just do this. We'll go through the calculations of, if everything works out, what is the time complexity going to be? And hopefully convince ourselves that, oh, this should lead to an L1/3 sort of algorithm. So here's what's going to happen. We are given an integer n that we are asked to factorize. Okay. our D is this whatever cube root of log n over log n or some such nonsense. So what we're going to do is we're going to take n and split it into like about D blocks, maybe D plus 1 blocks or something. Okay. And once you split it into that many blocks, I just told you how to build this polynomial f and find a number m such that f of x is equal to 0 mod. Okay. And the number field is going to be qx quotiented with f of x. Again, I'm hoping that f is irreducible and this number field is as nice as you want. Like you have a complete description of what the units are, all of those things, all of those nice things happen. Okay, then we're going to fix a suitable smoothness bound. Okay, and now what we're going to do is we're going to find all sorts of pairs, AIs comma BIs, such that AI and BI are co-prime. This is just for one minor technicality, such that AI minus m times BI happens to be B smooth. And previously I said I want this whatever number field element to be B smooth. Now I'm just going to say I just want the norm to be B smooth, because in order to factorize this, I just need to know what are the prime factors of the norm, and that's what I'm going to do this filtering. Okay, so try to find pairs AIs comma BIs such that this is B smooth and this is B smooth. Okay, use that to somehow factorize both of them. The actual algorithm doesn't factorize it. It does a slightly different thing with some extra fluff factors because of the units. But let's just assume that we factorize them. Okay. And now you again build your matrix based on exponent vectors, take the corresponding x's and y's that you get out of any such combination, and then the rest of it is as usual. Okay, is the high level picture now clear? I mean, like what we are going to do? The norm is going to play a very important role here, because if all our factorization starts with the norm, you first factorize the norm, which you know is an integer, because these AIs and BIs happen to be integers. And you're now hoping that, the factors of the norm will tell you what the actual factorization of alpha AI minus alpha BI is. So far, so good. Okay. And now we are just going to do the calculation of if everything works out. I mean, like there's a lot of things I don't really know how to factorize. I don't know how to handle units. I don't know what to do if the number fields are ugly, etc. But assuming all of them work out, okay, let's figure out what sort of bounds do we get. I mean, what is the running time analysis? Okay, again, I'm going to choose D to be our fantasy D that we had, which is to just take something like cube root of log n. So let's write this n power 1 over d slightly differently. So I'm going to write this as 2 power 1 over d times log n. Okay, I'm just writing n as 2 power log n. Okay, and what is this going to be? So this is going to be 2 power. So I have a log n, but I'm dividing by log n to the 1/3. So I'm going to be left with log n to the 2/3. So this is going to be 2 power log n to the 2/3 times log n to the 1/3. Okay, which we know this is like L 1/3. Sorry, L 2/3. Right. I mean, again, I don't care about the constants that are involved at this point, because we are doing a first order analysis. Is it okay so far? I mean, like, I hope this is okay. So now I need to get a sense of, okay, I said, let's try out various choices of AIs and BIs. And let's choose our smoothness bound to be something. Now I need to put numbers to them. Okay. And let's say that AIs and BIs are both going to be, let's say, at most L 1/3 or something. And B is also like L 1/3. Okay. And let's ask ourselves, what sort of numbers do we end up dealing with? Okay. Okay, how large is AI minus MBI going to be? So again, this is going to be roughly what M is as well. because the choice of m was also roughly n power 1 over d, if you recall what was happening here. Now, AI is at most L 1/3, BI is at most L 1/3. This M is like L 2/3. So this is roughly going to be like L 2/3. Okay, which is like, again, n power 1 over d. Okay. Now, what about norm of those numbers? Because that's also something I want to be smooth. So how large are those numbers? What is the norm of this going to be? This is basically going to be equal to fd times ai to the d plus fd minus 1 times ai to the d minus 1 times bi plus blah, 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 plus f0 times bi to the d. Okay. What's the size of each of these things? That's about n to the 1 by d. The coefficients that you will end up with. That's about n to the 1 by d. Each ai is like L to the 1/3. Okay. So you will basically end up with something that looks like exponential in, or rather, okay, let's give this a name. Let's call this capital A, and this is anyway capital B. So roughly speaking, the size of this number looks like something like A power D. Is that okay so far? I mean, it'll roughly look like A power D because each of these AIs and BIs are at most capital A, and I'm raising them to the power D. So therefore, it'll roughly look like A power D. So what is A power D? It is exponential in D times log n to the 1/3 log n to the 2/3. Because that's what capital A was. Capital A was log n to the 1/3 log n to the 2/3. That raised to the power D. So I have an extra factor of D here. And D is roughly of the order of, cube root of log n. So this will basically be exponential of log n to the 2/3 log n to the 1/3, which is roughly L 2/3. Okay, and this again is roughly n power 1 by d. So where are we so far? We did some weird number field business. We needed to find a whole bunch of pairs such that this number is B smooth and this number is B smooth. Okay, and it so happens that for the choice of numbers that we have, both the numbers that we are checking for smoothness is roughly of the order of n power 1 over d. Okay, and so if you think about how many samples do you need until you get a smooth congruence, you are looking for numbers of the range of L 2/3, and you're asking how many of them are expected to be L 1/3 smooth. And if you work out exactly, this will also be another L 1/3. So basically what I'm trying to say is that the fantasy that you wanted, which is that you want to run a factorization algorithm to factor a number capital N, and you somehow want to make sure that all the numbers you are testing for smoothness roughly looks like n power 1 over d. And somehow you are in a regime where all the numbers you're dealing with is like n power 1 over d. Okay, so hopefully it gives you at least a high level picture of why this, if everything goes well, I mean, if all the other technicalities don't happen, that you will end up with a factoring algorithm that runs in time L 1/3. Okay, so the theorem that I just want to end with is not really a theorem because, I mean, everything is a heuristic. Let's say, the heuristic is that we have an algorithm to factorize n running in time exponential in log n to the 1 by 3 log n to the 2 by 3. Okay, again, I'm completely ignoring the constants, because I mean, we are in a situation where we're just trying to understand the high level picture. Obviously, once you know that this algorithm works, you can try to throw all sorts of optimizations. You can actually start doing the sieving process, etc., etc. And all of this has been done by a whole sequence of papers, etc. But at least hopefully it gives you a sense of why the number field sieve, gives you something like L1 terms. Okay, so there's clearly a lot that has gone into it. So let me just break this down, in a short this thing. So the reason the number field sieve happens to be effective is that number fields happen to have a lot of similarities with integers in terms of factorization, in the sense that there is a notion of integers within them, firstly, and those integers have a notion of primes, and things do decompose into a finite set of primes, in a finite product of primes. It's just that there are technicalities, like the integers may not be what you want them to be. I mean, they could be ugly things which happen to be integers, or they could be, all sorts of units. Like there could be many elements that are integers but are still invertible, even within integers, etc. But assuming those issues, etc., don't happen, it at least seems to give you a way of factorizing. I mean, you're basically, all of these algorithms was doing the same thing, right? You started off with AI squares. AIs were in your control, and mod n, they happen to be equal to yi. So in some sense, you have two different factorizations, and you are somehow trying to find a product of them such that they're both squares and they happen to be equal. You're doing something very similar here, except the left-hand side and right-hand side are in different worlds. This AI minus MBIs are over the integer world, and AI minus alpha BIs are over the number field world. But you're still hoping for some way in which a suitable product of these and a suitable product of these both happen to be squares. So that was the first step. This is all the data collection step. And if you can somehow manage to do this, there is a way to move from the number field world to the mod n world by just substituting all alpha equal to small n. And that gives you a way of moving from the number field world to just z mod n. So now you have a product, you have two squares that happen to be equal mod n. And you are again hoping that, okay, now therefore x plus minus y should hopefully have a non-trivial GCD with n. Okay, that's the reason why you are doing all of this. But one of the reasons that makes this work is that turns out over the number field, you can sort of do your factorization. And the norm is very, very helpful in that process, because the norm is something that happens to map prime numbers to prime numbers. Well, sort of. Okay, like if you ignore those, the standard primes, all of these non-standard primes end up getting mapped to prime numbers. So therefore, when you're factorizing things, you don't need to try out all possible primes and wonder which primes divide this. The factorization of the norm will tell you what the norms are of the primes dividing this, and then your search becomes far simpler, and you can find those things. And all of this is able to help primarily because you are now in a position to deal with numbers of far smaller magnitude than you could in the quadratic sieve or Dixon's algorithm or the Brilhart-Morrison approach. Now the numbers can be as small as n power 1 over t, which is something that we had no way of doing in the other approaches, etc. And so in some sense, once your numbers are small enough, your optimizing parameters happen to be different. And if you plug in the right sort of things, you seem to end up with L1 terms. Okay, so that's all I wanted to say. I mean, I'll try and add some notes about the number field sieve, but they will all be on a high level thing, because I mean, this is a huge, an entire area of its own. So there's a lot of mathematics that goes into it, etc. And I'm just trying to strip off as much detail as possible to just give you a high level picture here. But hopefully it gives you a sense of how these factorization algorithms work. Okay, so that's all I wanted to do today. So we don't have any more classes in this course. I'll just have an office hour, an optional thing in case people have questions or people want to go over some problems in the problem set, etc., which we'll do in the next Tuesday, the usual scheduled session. And then we'll have an exam on Thursday, and that's it. Okay, so let me just stop here unless there are some questions, and and so on. Okay, cool. So then those who want to meet on Tuesday can meet on Tuesday.